Hello everyone, I am Mark Edward Gonzales from the Salle University's Peer Tutor Society or DLSU PTS. In this lecture video, we are going to walk through some problems related to related rates. One of the topics discussed in CS Math 1, that is differential calculus for computer science students. CS Math 1 is one of the courses usually taken by our first year students during their second term of stay at the university. So if you're watching this video, you're gonna take this course next term. So let's begin without further ado. Okay, for our first problem, we are going on a more biological flavor. This one is taken from Leithold's The Calculus 7 or TC7 as it's fondly called. Suppose that a tumor in a person's body is spherical in shape. If when the radius of the tumor is 0.5 centimeters, so radius 0.5 spherical, the radius is increasing at the rate of 0.001 centimeters per day. Now, what we want to find is the rate of the increase of the volume of the tumor at that specific time. Alright, so in most mathematical problems, the good first step is to begin by picturing the problem or having an accurate diagram. So let's have an accurate diagram first. It's spherical in nature, so it's rather straightforward to draw it. Good thing it autocorrected. So it's a nice looking circle, sphere over here. Okay, so let's have the variables. What are the variables of interest in this problem? In most related rates problems, and in virtually everything that we will be encountering in the CS Math 1 course, time is always a variable of interest. Why is that so? Because in related rates, we are typically dealing with two or more variables that are changing at the same time, albeit at different rate. So T stands for time. More formally, it's the number of days since the tumor started to enlarge. But let's just deal with time for simplicity. Let's just call it time for simplicity. Next variable. Here, we have the radius of the tumor. So R stands for the radius. Next variable, V, the volume of the tumor. Let's be a little bit more precise here and say that R is the radius of the tumor at time T, and V be the volume of the tumor at time T. Let's label this as R. Okay, now all our variables are in set. Let's deal with the given. From the get-go, we see that this sentence over here contains our given. If when the radius of the tumor is 0.5 centimeters, the radius is increasing at the rate of 0.001 centimeters per day. So when R is 0.5, we just omit the units for simplicity. Then dr dt. Remember, it's the rate, and derivatives are rates of change. That's why we are dealing with a derivative over here. 0.001. Okay, so far so good. Now, what are we required to find? We are required to find the rate of the increase of the volume at that time. So let's just say it's dv dt. Again, it's the rate derivative at that time. Okay, now that we have translated our problem, the keyword is related. How are the rates related? To be more precise, how are R and V related so that we can relate the rates also? It's something like finding the equation to relate R and V, and from that equation, finding a way to relate dr dt and dv dt. But let's put it in action. Let's call it the relationship. So the relationship here is an equation or perhaps a mathematical model. Okay, we want to relate R and V, volume and radius. Volume, we're looking at a sphere over here, so that's 4/3 pi r cubed. So we found a way to relate R and V. Now let's find a way to relate the rates, the dr dt and the dv dt. How do we do that? That's correct, by taking the derivative. So in this particular problem, we will be dealing with implicit differentiation. And in all related rates problems, we will be dealing with implicit differentiation. It is a nice idea to have a strong grasp of this topic first before delving into problems involving related rates. So let's perform implicit differentiation here. With respect to t, that's time, dv dt. Let's take the derivative of 4 thirds pi r cubed with respect to time. Let's do it step by step so that we will avoid errors. So this is a 4 thirds pi r cubed over here using the power rule will be 3r squared rather multiplied by dr dt. Cancel. 4 pi r squared dr dt. So now we have found an equation that relates dv dt and dr dt. And going back to our given, what do we know? So dv dt is equal to 4 pi r squared dr dt. So let's here. R is 0.5. So 4 pi, our R is 0.5. Let's make this a little bit thinner. Our dr dt is 0.001. Okay, let's simplify 4 pi. This is a 0.25 over here. This is a 0.001 here. Simplifying this thing, 4 times 0.25 is 1, or we can visualize it as 25 cents times 4 is 1 peso, or something like that. So 1 pi times 0.001 will give us 0.001 pi. Let's affix the units. We're talking about centimeters a while ago in this problem. So that's cubic centimeters for the volume. The rate, the time is in days. 0.001 pi cubic centimeters per day. And that is the, whoa, that's a weird autocorrect. And that is the, okay, that is the rate of the increase of the volume of the tumor at that time. So this is our introductory problem for this video. Now, while we ponder on the solution over here, it might be interesting to point out some temptations when we're doing related rates problem. So, what's temptation number 1? Let's place it here. The first temptation here is drawing the figure. As I draw the figure, you might notice that we deliberately use the variable r. Why not just use r equals 0.5? Will it cause the world to burn or cause the world to crash? Let's see. Okay, this figure is a bit misleading. Why? If we go to the relationship, we might be tempted to thinking that 4 thirds pi r cubed, so I'll just substitute my 0.5 here. Okay. And 4 thirds pi cube is 5 cube is 5 times 5 times 5, that's 0.125. But wait a minute, where did the r go? The r vanished. And without the r, how will I have my dr dt? How are we going to use this dr dt over here? So we see the first problem here. Let's pause and think why this is a problem in the first place. Looking back at the problem, it's very important for us to analyze the semantics. When the radius of the tumor is 0.5 centimeters, it doesn't say that the tumor has a constant radius of 0.5 centimeters. No, the problem tells us that at a specific point in time, the radius is 0.5 centimeters. And when, at that specific time, the radius is 0.5 centimeters, the dr dt is 0.001 centimeters per day. Again, there's a subtle difference between having it as the constant radius versus knowing its value at a specific time. So that is why in the figure, we opted to use the variable r instead of having a 0.5 right here. Because again, this 0.5 over here, we cannot overemphasize this. It's just the value of a variable at a specific time, at a specific point in time. It does not refer to the constant radius of the tumor. It is just, again, it is just a known value at a specific time. So this is a temptation, a wrong temptation when doing related rates problems. In short, when we're doing related rates problems, we first find the variables, then go to the given, then find the relationship. And once we find the relationship, that's when we perform the substitution of the known values. We do not perform the substitution of the known values before taking the derivative. We should take the derivative first and then substitute the known values. So not the other way around. Again, derivative first before substituting the known values. Do not substitute the known values before taking the derivative because that might lead to some erroneous lines of thought. Let's now go to the second problem. This one is the classic leaning ladder problem. So a ladder is 25 feet long. Oh, again, this one is from Lightholtz, the Calculus 7, the leaning ladder problem. A ladder is 25 feet long and leaning against a vertical wall. The volume of the ladder is, the bottom of the ladder is pulled horizontally away from the wall at 3 feet per second. Suppose that we wish to determine how fast the top of the ladder is sliding down the wall when the bottom is 15 feet from the wall. So this is actually Lightholtz's introductory problem to related rates. Okay, as with the first problem, our first step here is to draw a figure. Let's draw a good figure over here. It might be good to transfer this just a little bit to the right, just so we can clear up the screen. Okay, now we have a clean space for our solution. Ladder is 25 feet long and leaning against a vertical wall. Let's have the vertical wall as this. Okay, that's our vertical wall. Let's make it just a little artistic wall. Okay, then let's have the ladder that's 25 feet long. Ladder, bottom of the ladder. Okay, so we have this over here. Question, can we already have this as 25 feet? Yes. In this particular problem, we can already label it as 25 feet because this 25 feet over here is a constant. It's a constant as opposed to a known value of a variable. The ladder is always 25 feet. It's constantly 25 feet at all time points in the problem. So it's constant. Therefore, we can have it as part of the figure. So again, a very important difference when we're doing related rates and one source of confusion when we're first doing this kind of stuff. So 25 feet long, leaning against a vertical wall. So the bottom of the ladder is pulled horizontally away from the wall at 3 feet per second. Suppose we wish to determine how fast. Now, going here, 15 feet from the wall. Is this a constant or is this a known value of a variable? Let's look at the semantics. When the bottom is 15 feet from the wall. So it tells us that the bottom is not always 15 feet from the wall. Rather, there is just a specific time when the bottom is 15 feet from the wall. Therefore, we should not label it as 15 over here. Instead, we opt for a variable, let's say x. And let's say the vertical wall over here, let's just have this as y. Or to be more precise, this is this portion over here. Okay. Let's take a brief moment to analyze the figure over here. This is the x over here. And this portion over here stands for y. So y is the distance from the top of the ladder onto the bottom of the vertical wall. Again, y is the distance from the top of the ladder onto the bottom of the vertical wall. So let's have our variables to be more formal over here. Again, t is our time element. What's x over here? So x is the distance of the bottom of the ladder, that's this one, from the bottom of the wall at time t. So x is a horizontal distance. This one is a horizontal distance. Y is the distance of this one. This is the top of the ladder. Distance of the top of the ladder from here, from the bottom of the wall. From the bottom of the bottom. Sorry. From the bottom of the wall at time t. So this one is a vertical distance. Okay. We have our variables. What would be the next step? The next step would be to analyze what are given in this problem. So the 25 feet, yeah, we know it's 25 feet. Let's go for the more interesting ones. The bottom of the ladder is pulled away from the wall at 3 feet per second. Feet per second, it's a rate, it's a derivative. So the bottom of the ladder pulled horizontally away. So is that dx dt or is that dy dt? Yes, that's dx dt because it's the bottom of the ladder. The rate at which is being pulled is 3 feet per second. So 3. Let's just omit the units for simplicity. Do you have any other given? Wala na. No more given. Okay, let's go for it. What are we required to find? What do we want to find? We want to find how fast the top of the ladder is sliding down the wall. So we want to find dy dt when the bottom is 15 feet from the wall. That means when the bottom is 15 feet from the wall, when x, that's the horizontal distance, is equal to 15. So dy dt when x is equal to 15. That will be our equation for this problem. Or rather, that will be what we want to find for this problem. And now, as we did a while ago in our earlier problem, variables given, the next one would be the relationship. How are we going to relate these variables together? Let's go for the relationship. Excuse me. Alright. So, this figure over here is very suspicious. It looks like a right triangle. It is a right triangle. So, the very famous theorem with respect to right triangles is Pythagorean theorem. So, x squared plus y squared is equal to 25 squared. Leg squared plus leg squared is equal to the square of the hypotenuse. Okay, let's simplify it a little bit. X squared plus y squared equals 625. Okay, do a little bit of transpose over here. Let's have y squared equals 625 minus x squared. Might be wondering why. Well, let's make this thinner. We're looking for dy dt anyway, so why not isolate y as early as now? But if we don't isolate y, it's also okay. What's important is that we wiggle our way to solving this problem. But since we're looking for dy dt, it's a good idea to isolate y already to the left-hand side of the equation. Now let's take the derivative of this one again using implicit differentiation. So the derivative of y squared with respect to time, power rule, put back our yellow pen, 2y multiplied by dy dt. 625 is a constant, so that would be a 0. X squared, so that would be a 2x multiplied by dx dt. Let's simplify our equation. Dy dt is equal to negative 2x multiplied by dx dt. So that means I can cancel out the 2 over here, cancel. Okay, so step by step to minimize the chances of error. Negative x dx dt. What are we looking for again? We're looking for dy dt. So we just want to isolate dy dt alone. So dy dt will be negative x over y multiplied by dx dt. And finally, we have found a way to relate our variables together. as is the goal of related rates. So let's see how we're going to solve this problem. Let's now plug it in to our equation. So our equation is dy dt is equal to negative x over y multiplied by dx dy dt. Okay, dy dt are required to find. Dx dt is equal to 3 and x is equal to 15. So negative 15 over y dx dt, that's 8. Here we have a little bit of a conundrum here. How do we solve for the value of y? We don't know y. Okay, maybe we need to take a step back and try to see. Going back to our relationship, x squared plus y squared is equal to, so let's have it here, using a white pen. So x squared plus y squared is equal to 625. Well, when x is equal to 15, what will be the value of y squared? Okay, let's transfer this here so it doesn't get in the way. So y squared now will be equal to 625 minus 225, that's 15 squared, 400. So that means y is equal to 20. We take the positive value since we're talking about geometric figures. So again, what did we do here? We used the Pythagorean theorem over here in order to solve for the value of y. When x is equal to 15, when x is equal to 15, what's the value of y? When x equals 15, what is y? Then we get that y is equal to 20. So now we can use this for our equation. So negative 15 over y, that's 20 multiplied by 3 over here. Okay, just a recap. X is 15, y 20, dx dt is 3 as we found here. Okay, let's just go to see the bigger picture. Okay, makes sense. Negative, let's simplify this fraction. 3/4 multiplied by 3. Alright, that's negative 9/4. And that's our dy dt. So we're talking about feet per second in this problem. Feet per second. Okay. For the curious, why do we have a negative value for the rate? In physics, usually negative values are associated with things going down. And it does make sense. The distance decreases. The y value decreases with time because the ladder is sliding down. So this negative value over here, negative sign, indicates that y is dy dt. So y decreases as t increases, which makes sense because, again, as we have stated a while ago, this ladder over here, our ladder goes down with time. So it slides down the wall as time increases. So there we have our second problem, the leaning ladder problem taken from Lighthouse TC7. So it's negative 9/4 feet per second. Now let's take a moment to appreciate the bigger picture of the problem. So these are very interesting problems that span very useful applications across different disciplines. So again, just to recap, we need to accurately have a figure, name the variables, get the given, what are we required to find, what is the relationship. Here we use the Pythagorean theorem, and then plug in the values that we know into the relationship that we found. If in case we have some missing values, we have to be a bit creative and exploit the relationship that we have already found, or maybe use another relationship if we have to. For more complicated problems, we do have to use other equations. So we'll get into more of this later. Over here, then negative 9 feet per second. Then of course, we need to check if our answer makes sense. Here it makes sense to be negative since the ladder slides down. So in the next problem, we're going to take a look at a more complicated example of related rates.